Hi, everybody. This is the overview lecture that's to go with assignment 11. And this is where we're going to start in on calculus. So this is, I hope, a pretty exciting moment for you. Because, calculus has got a reputation as being like a difficult subject. It's not that bad. It's a set of tools that you can learn to deal with. And it's incredibly useful. Calculus is what you need if you want to deal with change, and the world is always changing. So, it's important that we be able to think well about not just static situations, but ones that are dynamic, where things are moving on us. You can also use calculus in static situations by just imagining something is changing. For instance, you're trying to build a bridge. Maybe the thickness of the girders involved is, you would normally think of that as a fixed number. But what if you imagined you could change it? And by changing that, you could then think about how strong is this bridge? How much weight will it
technological failure.
You can adjust the input parameter there, the thickness of the girders, until you get the maximum strength. And surprisingly, it's not always just make it bigger. Usually, often in real problems, there's a sweet spot you want to hit where you get the optimization of some quantity that's important to you. So calculus change. Now, you've seen a situation where change was sort of part of the picture previously when you looked at the slopes of lines. So yeah, the scenario where you have a line with a given slope. Remember the slope formula is you take actually you think of this as a change, right? You go from one point on the graph to another point on the graph, and in between those you have a rise and a run. That's what we normally call those things. But what the run is how the x changes. Run is actually a change in the input. And what the rise is the change in the output that corresponds to that change in the input. And that's really the concept that we want to have all the time, not just for lines, but what is the change in the output for a given change in the input. Now that usually depends on sort of where you're working. Not so on a line, though. On a line, no matter where you start out, if you change by a run amount, you'll get the same rise amount. That is, the slope on a line is always fixed. Well, what if we're not dealing with that kind of scenario? What if we're dealing with, something that's not a straight line? So here's a graph that I made up in GeoGebra. Very much not a straight line, some kind of weird S-curve. You can see the formula for this thing up here in the upper left corner. It's x cubed minus 6x squared plus 10x. Honestly, just more or less random numbers that I put in there. So this thing, if you wanted to have an idea of what its slope is, well, you get different rises and runs depending on what the 2 points are. Let's focus on a particular point. I've labeled it, or I've put it all in here already, 3, 3. Now 3, 3 happens to be right on the curve, but it's also nice because it's a grid point. There's a few other grid points on this graph, like up here. Well, I can't quite click on it because it wants to go to the extreme value. What is that? 1, 5 is a grid point, or this one. 2, 4 is a grid point. But let's look at our 3, 3. Now, you'll notice the way I have put that point in there is bizarre. I defined the function f, that is this weird polynomial that I put in, and then what I'm doing for the point is a particular coordinate, j, and then the function evaluated at that j. So this is guaranteed to be on the curve. Right? If I move j around, I get points that are just in motion along that curve. So this is how I could do what I was trying to do before. Not quite, because I set the bottom edge of the slider to 2. But anyway, there's another point that's on a set of grid axes. Now, let me go back to the one I kind of wanted to look at, which is here at 3. I'd like to be able to say, all right, how sloped is that line, right? How it's okay, it's not a line, but still there's some sort of angle involved here. So this next item I have on here, let me turn it on. That is a line that goes through that point, and its slope is determined by this slider M. It happens that M equals 1 is not bad. M equals 1 actually might well be the right slope to make this thing do what I want, which is more or less go in the same direction as the graph. But let's look at what it is if the slope is different from 1. Like here it is 2.5. Do you see how the green line hits the black curve in 2 different places then? That's kind of the usual situation. You try different slopes, you're going to hit the graph usually in 2 different places. Sometimes you'll do this kind of thing, which is really not what we want. You're hitting the graph only once, but moving in a completely different direction than it is. The slope along this line versus what I would think of as the slope along the curve are very different. But if you play with the slope of this line, you can just by eye come up with a value that makes this thing touch the graph once. I think it might be about there. M is 1.3 right now. So let me check that out by zooming in on this point. As I zoomed in a bit, I noticed something. In fact, this point, this graph, this line is not hitting the graph in just one spot. It's hitting it over here as well. You see the point way up there, the intersection of the line and the curve? So this M wasn't quite right. In fact, it looks like I want to do a smaller M. Then I get a line, another intersection point right there. Okay, smaller than that too. How about 1.1? Hard to set it to 1.1. Ah, there it is. 1.1. Now it's tougher to see, but there is also a second intersection point here. But if the value of that slope of the line is 1, we've really got the situation we're after. The curve and the line touch each other exactly once, and they're kind of going in the same direction at that point. When you have that scenario, that's called a tangent line. So let me go back to the DocCam view here. Curves don't have slopes, but they do have tangent lines, usually. And so what we do is basically figure out the slope of the corresponding tangent line and use that as the slope for the curve. Now, oops, there's some terminology that we need to learn. If you have a line that does what those ones where I hadn't gotten the slope right, you have some curve like so, and there's 2 points on the curve, and you've got a line that's going between those things. Such a thing is called a secant line. Versus if you have just a single point and the line is going in the same direction as the curve, that's what's known as a tangent line. And these two concepts are related in kind of a nice way. So let me transition back to GeoGebra here and put in some more of the stuff that I threw in here when I was fiddling with this. Let's see. First of all, I don't need to see the pre-approved tangent line there. What I'd like to do is turn on another point. It happens to be way outside our field of view at first. In fact, I should probably change this so that we're seeing these guys from a distance. Now, this other point is controlled in a funny way. So to take a look at how it was defined right here. Remember the point A had coordinates j and the function evaluated at j? This guy does the same thing, but where the input is j plus h. So think about h as being a little offset to the right. I've actually made this slider for h go from 0 off towards 0.5, so fairly small numbers, but they represent an offset in the x direction from our base point, which has j as its coordinates. See how in here it says j plus h? And then f of j plus h. The same trick I used before, no matter what I pick for this h, I've got something that's going to be on the graph. Now, this guy right here, this is a little bit tough, but this is the equation of a line that goes through both points. So let's figure out why the slope of this line is what I've done in here. But you see this piece of this fraction right here? F at, well, that's actually f at j plus h minus f at j divided by h. Why is that the slope of this line? Well, for a second, let's just say that is the slope of this line, and take a look at what we're getting here. I used x minus 3. That's part of the definition of if you know what the slope is. This is the what do they call this? The point slope form for a function, for a line that goes through 2 points. Well, for a line that goes through a particular point, I used the point j comma f of j as sort of the base point. But so this line goes through there, but it has the right slope so that it also goes through the other point. I hope that's sort of clear. Anyway, that's a thing you've done before, right? Come up with the equation of a line through 2 points. We're just doing it here where the points can be thought of as in motion, because that's the essence of what we need to do. We need to be able to think about how do we deal with change, and that means the points aren't static anymore; they're movable. I have to have these variables around. All right, so let me show you what we want to achieve. You have a secant line, but as you move that second point closer and closer and closer to the original point, what you get approaches a tangent line. Right now, it's not. In fact, if we zoomed in enough on there, you'd see that the 2 points that we're seeing are the intersection points, and in fact, there's a little gap between the curve and the line in between them. You really can't see it at this scale, but trust me, if we zoomed in enough, you would see it. I don't feel like zooming in, so I'm not gonna. What we want to do is basically bring the second point so that it's completely all the way. Whoops, I'm changing the wrong thing. Sorry. I better turn on the right slider here. It's for h. Let's move h around here. H is the difference in the x coordinates of those 2 points, right? As I move h towards 0, what's happening is the 2 points are drawing closer and closer together. And what happened just now? I made h actually go to 0, and everything disappeared. Right? When h was slightly different from 0, 0.01, close to 0, but not equal to 0, I had a nice line. But when I brought h equal to 0, it just disappeared. And you see how we've got a question mark here in equation 1? Let's examine where that slope came from in the point, in the point slope form for the line, and why has it gone wacky here when h is equal to 0. So for that, I suppose I should go back to doing some drawings on the other view. That's just a piece of a curve right here, and here's a point. Let's go ahead and call its coordinates x and f of x. So that's the trick you use to make sure that point with that x coordinate will be on the graph, because this is the function of y equals f of x. Oh, that's out of sight, isn't it? Sorry about that. Hiding behind my face. All right, so if I have a second point on this graph that's h over from there, that is, its coordinates will be x plus h, and this, wait, more parentheses. X plus h is the x coordinate, and f at x plus h is the y-coordinate. So let's think about what's the slope between those 2 points. That is, what is the rise and the run if we go from one of these to the other? The run is super easy because we're going from x to x plus h. So our run, it's h, right? Going from x to x plus h, we've changed by h. What is the rise? For that you need to subtract. You need the difference in the y-coordinates. And so that's going to be f at x plus h minus f at x. That's our rise. So the slope is just the fraction you get out of those 2 things. It's got h in the bottom, and it's got this thing f of x plus h minus f of x in the top. Now we're going to see that sucker a bunch, but right now all I need you to do is look at it and go, yeah, I see why when h is 0 we're in trouble. You got division by 0 when h is 0. So this thing explodes, or it's undefined. The slope is undefined at 0. Yet, what we're interested in is the slope when h is equal to 0. That's a problem. The thing, you can't calculate it, but you'd really like to know that number. Well, it turns out, and let's again come back to the other view in GeoGebra. So in this GeoGebra view, the thing had blown up when we let h go to 0. But if I move h away from 0, some values, hello, slightly different from 0, it's perfectly fine. And notice what's happening with the slope of this line as we let h approach 0. As I kind of creep in here, getting closer and closer to 0, doesn't it look like it's heading towards some particular value? That is, the slope is not changing a lot as we move in here. And I can kind of predict what it would be, even though the freaking line just disappeared on me, right? Where should it have been? Well, pretty close to where it is right now, with h at its tiniest possible value. The slider is set so that 0.01 is the minimum increment. But if I change the slider to go 0.001 as the minimum increment, I could get even closer. Well, that's the idea of a limit. And that's going to be the thing we attack in this first section. Figuring out what's the value of a function at places where you can't actually evaluate the function. All right, so the setup that we're really interested in is this finding the limiting value of the slopes of secant lines. So that's what this paragraph says. To do calculus, you're going to need to find the value that the slopes of secant lines is approaching as h goes closer and closer to 0. Said it in a slightly different way than I wrote it. But what we're going to do next, though, may seem confusing. So I wanted to point out what we're doing in order that you don't have this confusion. We're just going to examine the idea of limits in general. And then we'll apply that knowledge we gain from thinking about limiting values in general to this problem of how the slopes of secant lines approach the slope of a tangent line. All right, so here's the setup. You have a function, f of x, and you have a particular input value, x equals to a. And that's what you're interested in figuring out what f is doing as you approach x equals a. So the way that's written is this. You write the word lim, L-I-M, and usually people do it in cursive, but you don't have to. Underneath of that, you say, sort of describe how the limit is being done. And this bit where it says x arrow to a is read as x approaches a. So that whole first part of the symbol means the limit as x approaches a of f of x. So that's what it means. It's that expression, lim as x goes to a of f of x, means the value that f is approaching as the input value approaches a. That's right. Not x, but a. All right. So here's a couple of issues. There might not be such a value, right? You could have it might not be possible to decide what does it look like it's heading towards. Maybe it wiggles around infinitely often as you approach A. That's not typical. It's often the case that we can evaluate limits, but you need to know that it doesn't have to be that way. But if there is a limiting value, and in that case, I'm going to say this. We'll write the same thing. The limit as x goes to a of f of x. But we'll just name that something. Call it capital L for limit. If the limit as x approaches a of f of x is equal to L, then, well, let me unveil this a little at a time. There's three possibilities. What are those three possibilities? What I'm interested in now is we're in the scenario where a limit exists. It's equal to L. But there's also the function can be evaluated at A, right? Well, not necessarily. The function might not be defined when you stick A in. It might say, oh, I'm dividing by 0, like it was for our secant line example. A much more typical thing is that L and f of A just give you the same value. They're equal to each other. And the other possibility, third option, is you got both L and you got f of A, but they're not the same. So let's look at these cases a little bit at a time. Case 1, where f at A is undefined, that's the one we really care about, because that's what happens with the slopes of secant lines. As h goes to 0, the slope of the secant line becomes, well, it hopefully approaches some value, but anyway, when you get there, when you actually get to 0, you get an undefined thing, because you're dividing by 0. So this will be the scenario we care about the most. F at A is undefined, but there still is a limiting value of the function. F of x approaches L as x approaches A. That's how to say that. Case 2, very common. That is what happens normally. If a graph is just like a nice line that goes through a point, the limiting value and the value you actually get when you arrive there, they're the same. Case 3 looks strange, but one point to make is case 3 is in a sense the essence of humor. A lot of jokes rely on this idea that they're leading you towards a limiting value, but when you actually arrive there, it gets to be something else entirely. A case was made for that in a very good book about mathematics of humor, which I believe was called The Mathematics of Humor. Well, to discuss this a bit more, let's have a view at something in the book. This is a plot. Make sure you understand that this plot is made up, right? It is not an actual function. It is not a formula. This is just a curve somebody drew. But these behaviors that are illustrated on this sucker, they do happen. So let's look at the things I talked about. Well, case 1 is this one right here. It's above an x value, just slightly to the right of 2. So when x is maybe 2.1, the function is not defined there. That's why it shows an open circle there. The graph has a hole in it. But as you approach 2, from either side, by the way, you seem to be going to a limiting value, and it looks like it's 3. In fact, if you're in this scenario and you need to do this jump graphically, the value of the limit is what you would fill in if you wanted to fill in that open circle, the y coordinate of this open circle. This one over here, which is happening right above 1, that's the usual situation. The limiting value as we approach this guy from either side looks like it's 2, and that's actually the value of the function at that spot. Here's case 3. You've got, as you approach there, it looks like you're going to fill in this open circle and have a y coordinate of 1. Right? Either from the right or from the left, it looks like you're approaching 1. But when you actually arrive there, you get something different. So that's our case 3. Finally, this one is showing you one of the ways that it can happen that the limiting value it doesn't exist. There is no limiting value. The problem here is from the left, as we look at points moving along this graph, approaching the value of x equals 4 from the left, you get a value of 2, it looks like, on this horizontal line. But if you do the same thing from the right, you get a value of 3. I mean, how are you going to choose? You got 2 different limiting values, and so we just say the limit doesn't exist in that scenario. There's other ways that the limit might not exist, but this is the most typical thing when you're dealing with. And because of that, we're also going to talk about these 2 different ways of approaching our point. We can have the limit from above and from below, or from numbers less than a, through numbers less than a, and then through numbers that are greater than a. So we'll end this little discussion by showing you the notation for that scenario. So, here's the topic that I just mentioned, is left and right hand limits. So we'll start on the right hand one. The left hand one is very analogous, so let's just deal with the right hand. I'm sorry, when I was writing this, I got a little funky with my printing, but that probably should be a lowercase L there. Now it's even uglier. Anyway, the limit from the right, people also will call that the limit from above, is what you get when x approaches a through values that are bigger than a is. And here's how you write that. The limit as x goes to a, the plus means either from the right or above. Those are values larger than a. And if we have the scenario that I talked about before, where we're sort of an open circle, so the function isn't defined at this a coordinate. This would be x equals a, the vertical position that we're talking about. Well, really it's the horizontal position, but that determines a vertical line. Anyway, at x equals a, you have no value for the function. And kind of weirdly, it's immaterial what the value of the function is. You don't care about the function. You care about what's happening as you approach that x coordinate. And if you're doing that from the right, you're up on this piece of the curve, and you seem to be approaching a particular number. In fact, it's y equal to L. Let's call it L anyway. Notice that if you did the same thing from the other side, approaching it along this branch of the curve, you'd come to a different place. That location, let's call it L prime. That is, how do I point at this? That is written this way: the limit as x goes to a with a minus sign subscript of f of x. So you've got this idea of left-hand limit, right-hand limit, or limits from above and limits from below. And if those agree, then you've got a limit without any modifier on it. That's the upshot of that. Okay, so that was a bit of a long lecture. Sorry for the length of it, but we covered a lot of stuff. And anyway, hope you have a great rest of your day.